Next, we will introduce the topic of parametric equation. So let's get started. Let's suppose that we have two equations, or rather two functions. One is a function of t that represents the x value, and the other one is a function, also a function of t that represents the y values. And in such a case, we call t a parameter, and the collection of points whose coordinates x and y are given by this or can be computed by evaluating the function f and g. So this collection of points traced in a particular way so all that together is called a parametric curve. And we refer to the two original equations together as parametric equations. Which produce that curve. So again, we define two things here. We define the parametric curve and we define parametric equations. So first of all, let's specify what it means a particular way. So if you have 4 points, or any number of points, for example, these 4 points can be traced in many ways. But if we go from left to right, that will be one way, or we can trace the same 4 points from right to left, and that will be another way. So when we are dealing with a parametric curve, we always have a direction. So a particular way defines a direction. So unlike the graphs of functions that we have studied previously, so for example, let's say this is the graph of y equals x squared plus 1, which doesn't have a direction. The parametric curves do have a direction. So we can use the following language. The graphs of functions are static, and the graphs of parametric curves are dynamic. So we have some sort of motion associated with this image, right? So if the arrow points this way, so that means we can think of some particle and this curve representing its trajectory. So there are few things that we can do with parametric equations and parametric curves, and one of the things is we can sketch the curve given by the set of parametric equations. So for example, given this two parametric equations, let's sketch the curve. And if previously when we had to sketch a curve of, not a curve, but sketch the graph of a function y equals f of x, how did we do it? We considered the values of x as inputs, and then we evaluated y at each input, and by doing so we produced the ordered pairs, which we then plotted on the xy coordinate plane. So this is how we've done graphing previously. So what changes? We're still going to use the same idea. So when you have a function, it does make sense to evaluate it for different inputs. However, with differential equations, we have two functions. So for different values of t, we can evaluate x of t, and simultaneously we can evaluate y of t. So x of t is equal to t plus 1, and y of t is equal to t squared. So we can pick some values of t and compute the x and y functions for those values of t. So when t is equal to -2, x of t will be -1 and t squared will be 4. When t is equal to -1, we get 0, 1. When t is equal to 0, we get 1, 0. When t is equal to 1, we get 2, 1. And when t is equal to 2, we get 3 and 4. So as a result, what do we have? We now have, for each value of t, we have a point on the xy plane. So when t equals -2, we have a point -4. When t equals -1, we have a point 0, 1, and so on. And what can we do now with these points? Of course, we can graph them. So let's imagine we have the xy coordinate plane. And let's plot these points. So let's introduce the axis. So we have -1, 4, 1, 2, 3, 4. So this is t equals -2. When t equals -1, we have 0, 1. So this is our t equals 1. I'm sorry, -1. This is our t equals 0. And then we have 2, 1, which is right here. That's t equals 1. And then we have 3, 4, which is t equals 2. So now we can connect these points, and if we do it like this, the sketch is incomplete. Why? Because remember, the parametric curves have the direction. So direction is determined by in which I guess direction the t values increase. So we advance from smaller t values to larger t values. So in this case, we go from t -2 to t -1. So the curve goes this way, right? So we're going to identify the direction with arrow or arrows, as many as we need. So we completed the sketch of the curve. With the addition of a constraint for the parameter t in the form of an inequality, such as this one, we now have the curve that has a starting point. So this curve starts at -1. So this is what we'll refer to as the initial point, and the curve will end at what we would refer to as the terminal point. And now when you graph it, you graph only within the domain of this that's determined by the constraint on t. So this will be the graph of this parametric curve. Now, if we would like to check our work using technology, we can use Desmos, and the syntax is pretty simple. So you just put in parentheses as you are typing the ordered pair, but instead of x and y, we're going to type the equation for x and the equation for y in terms of t. And Desmos recognizes it as parametric equation, and it draws the parametric curve on this default domain. So now if we specify this according to our problem, then we get the exact picture that we produced by hand. However, Desmos makes it directionless, so it doesn't do arrows. So arrows have to be done by a human, I guess, in this case. But anyway, this is how we can analyze any set of parametric equations and sketch the parametric curve associated with the set of those equations. Alright, so let's sketch another parametric curve. So this time we're going to have some trigonometric functions, and here's the domain, and let's sketch this curve. So to sketch it, we are going to do the same thing. We're going to pick some values of t, and for each value of t, we're going to evaluate the sine of t, or rather, let's start with cosine of t and the sine of t. So we're going to pick the values of t strategically to make the computation somewhat easy. So let's start at 0. Cosine of 0 is 1, sine of 0 is 0. Let's move on to pi over 2. Let's go to pi, and let's go to 3 pi over 2. And let's go 2 pi, and if you recognize the pattern, then you'll be able to sketch the curve. So what do we have so far? We have at t equals 0. So these are my units. And at t equals 0, we're actually right here. At t equals pi over 2, we are right here. And at t equals pi, we're here. This is t equals 3 pi over 2. And this is also t equals 2 pi. So if you guess that it's a circle, you guess it right. However, what we have right now is not enough to conclude that it's a circle, because it could be like maybe a rhombus or something like that. So we can also verify that it's a circle by using Desmos. Real quick. And it does look like a circle. Yes, it is. So let's finish the sketch. So remember, Desmos isn't going to show us the direction, but direction is determined by the values of t. So we're clearly moving in this counterclockwise direction. So we sketched this graph. So what I want to point out here is that if we change the domain from 2 pi to 3 pi, we are going to get, what seems like the same curve, but it's not the same curve. And Desmos fails to recognize that. However, you should know that when t is equal to 3 pi, so let's see what happens when you advance another pi. So from 2 pi, let's go to 5 pi over 2 and 3 pi. So what's going to happen is that we're going to go a loop, and then we're going to advance another half of the loop. But if we look at it as a static image, we won't be able to see that second half of the loop. We only see like this projection of a circle on the xy plane. But the parametric curve, again, is not just the projection, it's a dynamic, I want to say dynamic image, but dynamic image means static, so it's a dynamic kind of process. And again, the best way to probably visualize this particular curve, it's like thinking of it as this. So it goes like this, and it goes on the second loop like this, right? But again, we don't see it as two different lines. One sits on top of another. Here's another example of a non-trivial set of parametric equations. So let's change it up just a little bit, and let's try to figure out the parametric curve associated with this set of parametric equations. And if we use Desmos here, which we can totally try, what is it going to look like? So it looks like this. And again, is this the entire image? Is it everything that we need to know? Well, actually no, right? So this is just like a static screenshot of the parametric curve. To actually know the parametric curve, we need to figure out the initial and the terminal point and the direction. So let's produce the graph by hand. So we're going to evaluate it at some values of t. When t is 0. All right, and what do we get here? So when t equals 0, we are at 0, 1. So let's introduce the scale here. So we are here at t equals 0. Then at pi over 2, we go to 1, 0. So now we're here. Then at pi we go, interesting, we go back to 0, 1. So that's pi. Then at 3 pi over 2 we go to negative 1, 0. And at 2 pi we go back to 0, 1. So we have an interesting situation here. Our initial point and terminal point are the same. So it starts and ends here, but it does it in an interesting way, right? So first it goes from here, then it goes back. It's really hard to draw this parametric curve, so it goes back, comes here, and then goes back here in this direction. So parametric curves are a little bit more than just the static images of functions. They are dynamic. So the next question is whether it is possible to figure out the parametric curve without doing all this what looks like a lot of work. So can we find the parametric curve somehow differently? And the answer is sometimes it is possible. So in this case, let's take a look at this system. Well, it's not a system of equations, but we can totally view it as a system of equations. And when you do that, you get this idea that we explored while studying systems of equations. We can try to maybe isolate certain variable. Like in this case, we can use the first equation and isolate t, and again, in certain domain. So we have to be careful here with the domain, but t is equal to arcsine of x. Again, symbolically it makes sense. It may not make sense for all values of t here, but let's just stick to it. And now once you isolate t symbolically, what you can do is you can replace t in the second equation with the expression that you obtained in the first equation for t. And what have we achieved by doing this? We actually ended up with an expression for y in terms of x. So this can be thought of now as the function of x. And why is this an advantage, or where can we go from here? This is an advantage because we actually are more familiar with functions given to us this way. We studied a lot of functions in trigonometry and algebra or pre-calculus, so we are trained to recognize and graph functions given to us in this form. However, this particular function doesn't look easy. However, it can be simplified using the technique that we've learned in trigonometry, and we also practiced it in some parts of calculus. So cosine squared of arcsine x can be simplified into well, it's going to be just 1 minus x squared, but why? Well, because if you take cosine of arcsine and call this theta, then we're looking for cosine of theta. But what is theta? Theta is such that sine of theta is equal to x. And if you draw a triangle with angle theta, then sine of theta equals x means we can label the opposite side x and the hypotenuse 1, and then by Pythagorean theorem the adjacent side will be equal to square root of 1 minus x squared. So cosine theta is adjacent over the hypotenuse, which is exactly square root of 1 minus x squared. And since we squared it over here, we're also going to have to square it over here, and that brings us to this answer. So the idea is that now that we know that this set of parametric equations is somehow related to this function. Somehow, right? So And what we see here is that this graph that we see on the right side is actually the piece of this parabola. So this green is the parabola 1 minus x squared. So what we have done here has the name. The name for this process is called elimination of the parameter. So by eliminating the parameter, we can identify the shape of the parametric curve, but we wouldn't know the initial or terminal point, and we wouldn't know the direction. So even after you eliminate the parameter, you still have to determine your initial point, terminal point, and direction. So let's try another example. Let's sketch the parametric curve given by the following set of parametric equations using the elimination of the parameter. So first I'm going to isolate t in the first equation, so t would be equal to x minus 1, and then I'm going to replace t in the second equation with the expression that we obtained for t. And as a result, we have now isolated the parameter, and we have the function whose graph represents the trajectory. However, just by graphing this parabola x minus 1 squared may not be enough. May not be, but like it's for sure not going to be enough. Why? Because we don't know the initial nor terminal point yet, nor we know the direction. So we have to find the initial point. The initial point will be when t is equal to 0. So it's 1, 0. And the terminal point is when t equals to 2. When t equals 2, we get 3, 4. So on the graph, this is our initial point, and the terminal point will be at 3, 4. So this is 1, 2, 3. This is 1, 2, 3, 4. So we don't need to graph the whole thing. We only need to graph this piece of the parabola. And one more thing we need to determine is the direction. So the direction here is clearly going this way. So we go from t equals 0 to t equals 2. Let's try another example. Let's eliminate the parameter for the following parametric equation, and here we are going to deviate from the original technique of elimination, and we're actually going to use the trigonometric identity that says that cosine squared t plus sine squared t is equal to 1, and therefore x squared plus y squared is equal to 1. So we don't get a function here, but we still get the trajectory which is a full circle. So again, the parametric curves are more than just functions. They have direction and initial and terminal points. So in this case, our initial point will be at 0. And the terminal point will be at 2 pi, which also seems like the same point, right? So we're gonna have to do something to figure out the direction in which the curve advances. So to do that, we're going to pick another value of t, and I'm going to pick, let's say, pi over 2. So where is it at pi over 2? So at pi over 2, we're going to be at 0, 1. So this is where we're at t, when t is equal to pi over 2. So the movement on this circle will be in counterclockwise direction. Now, the next question is, can we so what we achieved so far is we were able to take a set of parametric equations and produce the curve of some sort, right? And the question is, can we go in the other direction? So can we take a curve and produce the set of equations? And it really depends. So the answer depends. It depends on what we know about the curve. Sometimes we don't know enough, and then let's consider this example. Let's say we have a curve which is a part of this parabola. So it looks like this. It's from 0 to 2, right? So let's just consider this part of the parabola. And let's try to parametrize it. So let's try to create a set of parametric equations that produce the same piece of the parabola. And turns out that it's not that easy. We can do a trivial parametrization by setting x equal to t, and then y of t will be t squared minus 2t, but this parametrization is rather trivial because you can see that all we did is just replaced x with t. This parametrization is not unique. We can also replace x of t with something else, such as 2t, and then y of t will be equal to 4t squared minus 4t. And what's going to be different here is the parameter and the constraint on the parameter. So in this case, t will be ranging from 0 to 1, while here in this trivial parametrization, t will be, or t is ranging from 0 to 2. So the idea is that it's not an easy process, and in order for us to pinpoint one unique parametrization, we need to know a little bit more than just a piece of a curve. So let's consider the following example in which we will be able to parametrize the curve uniquely. So consider a particle that moves on a straight line from point A to point B, And let's say, so again, let's do a quick sketch here. We have -9, -7 somewhere here, right? And then we have -6, 5 somewhere here. So this is my point A, this is my point B. The particle moves from here to here, and let's say it moves at a constant rate. So if that's all we know, then there are many ways to parametrize this curve. However, if we also assume that it takes the particle 15 days to go from A to B, then we can pinpoint one unique parametrization. So let me show you how we can do this. First of all, we have to understand the motion of the particle. So if we independently look at the x and y coordinate of the moving particle, so here's the x coordinate, and here's the y coordinate. We'll be able to see that x advances from the x coordinate of point A to the x coordinate of point Y. So x advances uniformly from -9 to -6, while y advances uniformly from the y coordinate of A to the y coordinate of B. So if it takes 15 days to advance from point A to point B, that means the x coordinate advances, what would be the rate of change of the x coordinate? Let's call it the x rate. Or let's express it first. So in 15 days, we advanced from -9 to -6. So what do we have here? We have 1/5. So this is how it advances along the x-axis. 1/5 per day. And what's going on along the y-axis? Something similar. We went from -7 to 5. So the total change was 5 minus -7 is, what was it, 4/5 per day. So if you ask me where is the object t days after it started moving, we should be able to pinpoint it on this line segment. So if we let t be the number of days, since the start, then where is x of t? Well, we started at -9, and then we advance 1/5 per day, but we are t days into it now. So this is how we find the x coordinate at time t. It's very easy to check. Just set t equal to 0, you should be at point A, and set t equals to 15, you should be at point B. So similarly, we find the function that represents the y coordinate. We start at -6, no, sorry, -7, and then we advance it 4/5 of a unit per day. So in t days, we'll advance this much. And this is our equation, or rather the set of parametric equations. And the constraint on t value is that t ranges from 0 to 15. So this is a brief introduction to the topic of parametric equations. Next, we'll discuss some of its applications.